Section we're going to learn about graphing logarithms and how logarithms act, and what you really want to do out of this, just get a general idea of what log graphs look like, and what's the domain, and then we're going to reinforce some of that work we've done with transformations. In calculus, it's really important to understand what log graphs look like where the domains are, and then like what happens when you go out to infinity and all that. So let's get on with this. What you got to remember as we're tackling this stuff is that all a log is an exponential function rewritten, right? So if I have, let's see, f of x equals 3 to the x, that's the same thing as it's the inverse. It's not the same thing. I mean, so that work we did with exponential functions here. Let's do some graphing. So 3 to the x crosses it at 1, at the y-axis at 1, and it looks something like this, right? It starts growing like that. Now, if we were to ask when is 3 to the x equals 2, well, one thing you could do is you could take the log of both sides, right? So I'm going to take x times the log of 3 equals the log of 2, and then divide by the log of 3. Yes, I'm doing this for you, Becca. Divided by the log of 3, and then x equals log 2 over log 3. And then, I don't know if you remember back when we did change of base. Change of base was you take the log of a. If I'm looking for the log base a of b, that's the same as log b divided by log a. Well, if you see the a is the base, so in here this 3 is the base of this log. So I could think of that as, let me make some more room here. I could think of that as this new function, log base 3 of, now I'm losing track of what it was, of 2. Okay, and now your new graphing calculators will actually calculate that for you. There's a function that'll do that. A few years ago we didn't have that option, so we had to use change of base. But what I want you to see is this is the inverse, right? If this function here, if I'm asking 3 to the x equals 2, so I'm asking you when is the function equal to 2? Well, the inverse of that would be this. Would be 3 raised to what power is 2. And that's all this log is. So that's the inverse. Now, how this applies to a graph is, if you remember, inverse functions get reflected around the line y equals x. Here's y equals x. And if I do some plotting of this, let's see here. Let's go to a blue ink. And if this is 0, 1, that means the inverse graph is going to cross through 1, 0, because remember we're switching x and y. And so what that means is this graph is going to look like this. It's just reflected. You see how that's reflected? I mean, I could pick some other points, and I'm just switching the x and the y. I'm just switching the x and the y, right? So that's what a log graph looks like. And yeah, this 3 to the x, this 3 to the x grows faster than, say, e to the x. And what that means is log base 3, so yeah, I better make this a function. But this is the graph is log base 3 of x. Not just a specific number. That thing I did here was just the specific number. Okay, so the domain is from, x has to be greater than 0, because I can't take the log of 0. I mean 3 to if I had to find log base 3 of 0, well, this graph, right, 3 to the x, this says when is 3 to the x equal to 0. Well, 3 to the x is never equal to 0. That never crosses the x-axis. It gets closer and closer and closer, but it never gets there. And so that's just it. That's just it. This graph will never cross, the log graph will never cross the y-axis, unless it gets shifted around, and we'll look at some of those. But on a basic format, it will not. So the domain has to be x is greater than 0, and it's open because it'll never equal 0. Okay? Crosses the x-axis at 1, 0, and then it keeps growing. Now, it makes it look like a horizontal asymptote, but what happens is it just keeps going forever. Granted, it just starts growing very slowly, but it does keep going. It's not a horizontal asymptote. So the domain is x is greater than 0. The range is all real numbers, because this goes down to negative infinity, and it goes up to positive infinity, just really slowly that way. Okay, so now what we're going to do is look at a shifted function here. So remember how we were talking about a minute ago, how I can't take the log of a negative number? So for this one, basically what I want is I want to say, and I can't take the log of 0, I mean, also. So basically what I'm doing is I'm solving this inequality. When is 5 minus 2x going to be greater than 0? And it can't be equal to 0 because I can't take the log of 0. So that gives me this equation. I'm going to subtract 5 from both sides. So that gives me negative 2x is greater than negative 5. Then I'm going to divide by negative 2, divide by negative 2. So the domain is x has to be greater than 5/2. Okay, and that's how you do that. So you set it, just look at the middle, the inequality, the whatever's the inside the argument, we call that, and solve that. Now, so for the second problem now, what we're going to do is, let's see, they're telling us to look at it, consider the transformations. So I know that normally log graphs look like this. They cross through 1, 0. They have x equals 0 as a vertical asymptote. And this point is a special point because it crosses the x-intercept. So if we think about, so I'm seeing that this graph has been shifted right 5 and up 2. Let's think about what happens with this point. So I'm seeing it's been shifted right 5, so it's at 1, then 2, 3, 4, 5, 6 moves it to the right 5, and then it gets shifted up 2, so 1, 2, so right about there. And so I know this graph looks something like this, but then you notice how the y-intercept, the vertical asymptote here is at x equals 0. Well, that's also going to shift over to the right 5. So our new vertical asymptote is there, which I believe is x equals 5, right? 1, 2, 3, 4, 5. Yep, so that graph's going to look something like this. So they want us just to find the domain. So notice how the 2 didn't really come into play at all as far as the domain issue. So really all we're going to worry about is the same kind of deal. X minus 5 has to be greater than 0. So add 5, x has to be greater than 5, and that corresponds to what we thought graphically. Okay, so it's that argument really that makes it matters about the domain. There are variations in this, but for this basic format, that's all that there is. Okay. Textbook they show you this in this section. They talk about how the log of a different base of x can be written with a change of base. What they're trying to get you to see out of this is the only difference between, say, a log x and an ln x, or a log base 3 of x, is that there's some stretching going on, that it'll grow faster or slower, and you'll see some of this as you get into this. So they want us to graph this. Now, I know that logs go through the x-axis at a certain point, and typically they go through 1, 0 unless they've been shifted. So what I'm seeing here is that this graph has been shifted to left 2. So that's all I'm going to worry about at that point. I'm going to take that point and slide it to the left 2 units. So now it's at negative 1. And then I know my vertical asymptote is, again, unless there's been some stretching going on, is 1 to the left of it. And so then I'm just going to make a little sketch. It looks something like a log graph. And I mean, if we had a Desmo or graphing calculator, you could see how that's growing faster or slower than log or log base 3 or whatever. But that's basically all there is to it. Remember, all we're trying to do is get the general form of what these things look like. So I'll help you get this one set up, but then I'd really like you to stop the video and try to graph it yourself. So what are we seeing here? Well, I'm seeing a graph of log base 10, but that doesn't really matter. I'm seeing it's been stretched vertically by 5, and then something's going on in here. I see a negative, and usually when, I don't know if you remember that work we did before the exam, f of negative x means it's been reflected around the y-axis, right? So what we'll do with this is we're going to factor out. I'm going to rewrite this as 5 log of negative, and then what I did is I factored out a -1, which changes all those signs. Okay, so now I can see, okay, yeah, that's the reflection around the y-axis, or it'll be around the vertical asymptote actually. And then I see it's been shifted right 5, and then there's a stretch going on. So I'm going to shift it right 2. So instead of the vertical asymptote happening at x equals 0, it's happening over here at x equals 2. I know there's a stretch, but it's not been shifted up or down. And if you think about it, if I substitute in say 3, if I had this, if I had 5 log of x minus 2, if I substitute in x equals 3, what do I get? See, I'm predicting that this function here crosses at this point. If x equals 3, doesn't that give me 5 log of 3 minus 2? And 3 minus 2 is 1. Log of 1. What's the log of 1? Well, 10 to what power is 1? And they all said 0. So it does cross right there. Now, because it's been reflected, instead of crossing there, it's going to cross over here. Let's think about let's see, what do I got? Blue. With the unreflected graph would look like this. So the reflected graph is going to look something like this. See how it's just been reflected around that vertical asymptote? We could find the y-intercept by substituting in x equals 0. So 5 times the log of negative times 0 minus 2. Well, that becomes the log of 2, right? 5 times the log of 2, which is some wonky number. So we're gonna put that there, and that's going to be the graph of that function. Okay. Notice I didn't really need to do a whole lot of work other than thinking about how did the vertical asymptote change, where does it cross the x-axis, and then just made a little sketch. Okay. Try this one. I'll let you. You should stop the video, try it yourself, and then come back and watch it. So you could also look the answer up in the book, because this is a try it now. So let's see. I'm seeing a graph. What am I seeing here? So I'm seeing a stretch, vertical stretch. I'm also seeing a reflection around the x-axis, right? I'm seeing it's been shifted right 2 and up 1. So let's see, we can start doing this. Let's see here. So I know that typically this has crosses through 1, 0, but I also know for this graph it's been shifted right 2, then up 1. So that point's happening here. I know the vertical asymptote is at positive 2, x equals positive 2. So I'm going to draw that in just to give myself a reference point. And typically, and I know the vertical stretch just means it grows faster. So before I do the reflection, that's what that graph looks like. But now, it's been reflected vertically. Reflected vertically, right? So that tells me this graph is going to, instead of coming from negative infinity on up, it's going to come down like this. Okay. The other thing I would like to know and ask myself is, does it cross the x-axis? Does this function cross the x-axis? Well, if to figure that out, we know y equals 0. So to solve that, I'm going to subtract 1. Divide by 3. Then I'm going to rewrite this as an exponential because I don't know how that works out. So 10 to the 1/3, so I'm taking the cube root of 10, right? Equals x minus 2. So I'm going to take the cube root of 10 plus 2. Now, suppose I didn't have a calculator, I couldn't use a calculator. How do I figure out the cube root of 10? Well, I know 2 to the 3rd is 8. I know 3 to the 3rd is 27. So the cube root of 10 is somewhere between 2 and 3. Right? And then I'm going to add 2 to that. So that tells me this graph is going to cross somewhere between, let's see, between 2 and 3, and then I'm going to add 2. So it's between 2 to 3. So I'm going to add 2 to each of those. So that's going to be somewhere between 4 and 5. So 1, 2, 3, 4, 5. So it's going to cross somewhere here. So I'm just going to make a graph that looks something like that. Okay, so that's basically what this graph looks like. So now we're going to be writing equations from a graph. And what you want to pay attention to are these two basic forms of what it's going to look like. Now, if it's been reflected around the y-axis, it's going to look, remember how it's going to go up, head off like that, versus normal log graphs head off this way. That's what they're talking about here, that negative. And we can solve for all that. I mean, sometimes noticing that makes it easier. Now, before we do this, we should take a look at this graph and talk about the domain and range. That will help us solve this. So I'm seeing a vertical, so the VAs happening at -2. And so that means the domain is x has to be greater than -2. And I see the range, it's going as x goes to the left, as x approaches -2, y goes up to infinity, and as x goes out to infinity, y heads to -infinity. So I know that there's going to be some kind of negative f of x going on, right? I know that the number in front of our log is going to be a negative number because it's been reflected. So let's do some piecing together here. So I know the vertical asymptote is happening at -2, and I know that vertical asymptote comes from what's inside the argument. So I'm going to write this part of it. I'm going to write f of x equals a times the log of x plus 2. Remember, we're going to change the sign, plus some constant in case it's been shifted up. I don't know if it has. We're going to find that out. So some other things I'm noticing is it crosses the x-axis and the y-axis at 0, 0. And then I'm looking for some other points that are nice. Ooh, that's a nice point. -1, 1. And then to me it looks like it crosses at 2, -1. Maybe we can use that to check, or use one of these to find out. Well, I really want to be able to keep this as easy as I can to make my math easy. And I know if I take the log of 1, I get 0, right? And that might help me isolate. That'll help me get rid of this. If I have the log of 1, that'll help me knock out the a. Maybe I can find out if there is a k other than 0. So if I look at the points that I found, if I use this one where x equals -1, let's substitute that in. So 1 equals a times the log of -1 plus 2, plus some constant, maybe that's there. So 1 equals a times the log of, let's see, -1 plus 2 is 1, and the log of 1 is 0, so all this is gone, so k equals 1. So there's a vertical shift to this graph. So I can write this part of it. Let's see, so f of x equals a times the log of x plus 2 plus 1. So now I've got to find, the only thing I don't know is the a, so I suppose we can pick any other point. How about 0, 0? That's always a nice one to use. So y is 0, and x is 0. So I'm going to subtract 1, then divide by the log of 2. So that's what I think a is. So y equals, or f of x equals, -1 over the log of 2 times the log of x plus 2 plus 1. And that is the graph, or the equation, that gives us this graph. Okay, it's not too bad. I mean, try to find k if there is one, try to find a if there, whatever that is, and then usually pretty well done. So these are out of the textbook, right out of the exercises. These are even numbered exercises. If you want to try them before you watch, you certainly can. I'm gonna walk right through these now. So what am I seeing? Well, for this one, I know typically log graphs go off in this direction unless they've been shifted this way, and but this graph is headed off the other direction. So this tells me it's been reflected around that line, x equals 1. So if you go back and look at those general forms, I'm thinking that this graph has the general form of a times the log of negative x minus b plus some k, or whatever variables you want to use. All right, but I know there's going to be a negative inside that. So I'm also seeing that there's a vertical asymptote at x equals 1. So what I can probably do is write a log of negative x minus 1 plus some constant. Okay, and I knew this negative was in there because of that reflection. Okay, and so now let's pick some points here. So let's see, I'm seeing -1, 1. I'm seeing 0, 0. I might be able to use this one, -3, 2. Oh, let's see what's happening here. Remember, I'm trying to get this to be 1, because if I take the log of 1, that's 0. That'll knock out that a, and that'll help me see if there is any k number. So if I use 0, 0 here, if I say 0 equals a times the log of -0 minus 1 plus k, 0 equals a times the log of, well, let's see, -1 is +1, and the log of 1 is 0, so everything that tells me k is 0. So that tells me there's no vertical shift. So I'm going to write y equals, let's see, a log of -x minus 1. I'm going to forget all about my k. So now we can pick either of these points. What if we try -1, 1? Because that's a nice easy number to use. So -1 equals the log of -1 minus 1. So 1 equals a times the log of, let's see, -1 minus 1 is -2, change the sign. So 1 over the log of 2 should be a. So I'm thinking the equation in this equation is f of x or y equals 1 over log 2 times the log of negative x minus 1. And remember, k was 0, so we didn't need to include anything. So that's what I think the equation for number 17 is. Okay, so for number 19, to me, I think this has been reflected vertically. It isn't like this one, how this headed off to for as x goes to negative infinity, y equals positive infinity. This looks like it's just been reflected around either the x-axis or some other horizontal line, okay? That tells me the number in front of the log is going to be negative. Inside it's going to just be positive. So I'm seeing a vertical asymptote at x equals negative 4. So that tells me I can write y equals a times the log of x plus 4, been shifted left 4, plus some number k. Let's see, it crosses the x-axis at negative 3, 0. It crosses through, let's see, I'm suspecting I could use negative 1, negative 3. Let's see what we can do with that. So remember, I'm trying to get this, in order to find out if there's a k, if it's been shifted up or down, I'm trying to make this be the log of 1. If I use this point here, that will probably do that for me. So 0 equals a times the log of negative 3 plus 4 plus some number k. And negative 3 plus 4 is 1. The log of 1 is 0, so that knocks out that whole term. So that tells me k equals 0, so there's no vertical shift. So that leaves me with, let's see, can I erase some of this stuff? Yeah. So that leaves me with y equals a times the log of x plus 4. So now let's try using this point negative 1, negative 3. So y is negative. It's equal to, let's see, negative 3 equals a times the log of negative 1 plus 4. And then, so that gives me negative 3 equals a times the log of 3. So I'm going to divide by the log of 3. And that's what I think a is. That gives me f of x equals negative 3 over the log of 3 times the log of x plus 4. Here's 2 more problems. Try them. Come back and watch the videos. See if you can get your answer. They're also in the book. You can look your answers up in the back of the book. So I'm seeing a log for 21 here. I'm seeing a log function that's just been slid to the left too. It doesn't look like it's had any reflection done on it. So I'm going to write y, or f of x, equals a times the log of x. Remember, it's been shifted left 2, so I'm going to write plus 2, plus some number k. See if there's a k. Now we're going to pick some points. Well, I see negative 1, 0 is where it crosses the x-axis. I'm seeing this point looks promising, 3, 2, 3. So if I substitute in negative 1 here, that'll give me the log of 1, which will help me find k. So 0 equals a times the log of, let's see, so negative 1 plus 2 is 1, plus k. So since the log of 1 is 0, k also equals 0. So now let's use that 0.23 to see if we can't find that a value. So 3 equals a times the log of 2 plus 2. Well, let's see, that's going to be 4. So 3 over the log of 4 should be my a value. So y equals 3 over the log of 4 times the log of x plus 2. So I just graphed this on Desmo, and that looks like that does it for me. That looks like the same graph. So now try number 23, and I'll try it and come back and stop the video, come back and take a look. So I'm seeing a graph. Let's see what's been happening here. I think this has a double reflection going on. I think if it had been reflected around that to the vertical asymptotes happening at x equals 5, and if it had been reflected, or see, if it hadn't been reflected, it would have been over here, or reflected vertically, it would have been over here. But what I'm seeing is over to the left side and reflected around the x-axis or some axis. So there's going to be two double negatives in here. So to keep it easy, and remember back to that journal form, I know if it's been reflected around the vertical asymptote, I'm going to write y equals a times the log of negative x minus 5, because it's been shifted to right 5, plus some number k. Now I got to pick some points. Well, let's see. 4, 0 is a good one to pick. That should let me find k. So 0 equals a times the log of, let's see, negative times 4 minus 5 plus k. Well, that's going to be negative 1, which is 1. Log of 1 is 0. So k also equals 0. Now I've got to find another point. Well, this point looks very promising. 0, negative 2. Let's see what happens with that. So 0, made that mistake. Negative 2, sorry. So negative 2 equals a times the log of, let's see, negative 0 minus 5. So negative 2 equals a times the log of 5, I believe. So I divide by the log of 5. That should be what a is. So I'm hypothesizing that f of x equals negative 2 over the log of 5 times the log of negative x minus 5. So graphing that at Desmos, it looks like it's about the same graph. So I think we're good. Okay, so hopefully this will help you answer those questions now.